using Buckingham Pi theorem, determine the dimensionless P parameters involved in the problem of determining the pressure drop along a straight horizontal circular pipe. Okay, so our interest here is the pressure drop. Assuming that the pipe is smooth. So if the pipe is smooth, then that means we can disregard the fouling factor and the roughness of the pipe, which could influence, obviously, the pressure drop as well. So we can disregard that guy there. Relevant flow parameters are given, and they are the pressure drop that we're interested in. So let's just leave this in yellow. Then density, density, average velocity, viscosity, pipe length, and pipe diameter. Okay, so how many dimensionless numbers, pi groups, describe the problem? Write down the equations for these dimensional numbers and what are their physical significance. Okay, so we're going to start with the Buckingham Pi theorem. Okay, that says that the number of pi groups that I will have, that is the number of non-dimensional numbers, or let me rephrase that, quantity of non-dimensional numbers that we're going to have, equals the number of variables that we have, independent variables, minus the number of dimensions that we have for these variables. Okay, I'll just put independent here so that we are sure of what we're doing. So our variables are pressure drop, density, velocity, viscosity, length, and diameter. Those are the things. Okay, so we have 6 independent variables, right? 1, 2, 3, 4, 5, 6. Now, one thing to be aware of, if I wanted to, okay, for instance, you could tell me that, wait, but Pablo, the area, the surface area of the pipe also is going to influence on the pressure drop, and that would be fine. You could put area here, but then we're going to have to eliminate something else, because we know that the area is related to, is a function of diameter and a function of length, right? So that means it's not an independent variable. So right, and if it's not independent, then we wouldn't place it here along these assumptions, along these other variables. Same thing stands for volume and things like that. Okay, so what we have here is, if we want to find out the number of pi groups that we have, we're going to have those 6 variables minus the number of dimensions. And to find the number of dimensions, what we do is we look into the units of all these guys and to see what are the different dimensions that we have. Okay, what are dimensions? Well, that's the fundamental dimensions we work with. So we have mass, we have length, we have time, we have temperature, and then we break them down. So let's do that. Let's break it down. We break down each of our variables in terms of their dimensions. Now, if you guys are used to, that's correct. Yes. So if you're using volume, you wouldn't be able to use density. Yeah, precisely because density is a function of volume. So you would be either or. 100% correct. Yes. Okay. So if you guys are very comfortable using SI units, you don't really have to convert into dimensions. You can leave it as units, and that's usually what I do, because I find using the dimensions is more confusing. But I'm going to stick with what the convener is using in this unit for you guys, and what is the general practice when we're doing this. Okay. So we know unit for pressure is Pascal, which is newtons per meter squared, right? Well, we can break down newtons because we know newtons is force is mass times acceleration. So mass is kilograms and acceleration meters per second square. So we have meters per second square, and then we have this meters per square on the bottom. So we can get rid of these guys, and we're left with kilograms per second square meters. Okay, so you could leave like so if you wanted to work with SI units, but if we're breaking down into dimensions, what would happen is, this is the dimensions that we have here are mass, m for mass, then we have time square, and I'll put ti, I'll tell you why in a second, and then m is meters, and that is length, right? So it'll be mass over time square over length. Those are the dimensions that we have in the pressure drop. Okay, now the reason why I generally avoid using this and prefer keeping this is because it can get confusing when we have m, right? Because we have m for meters and then m for mass. That's something that can get in your way and can get confused about. The other thing is that we usually use T for time and then K for temperature or theta for temperature. because T and temperature and time both T, right? And that's why the reason why I put the little I there, because as we're learning this for the first time, it's probably best to have that so that we're not confused. Okay, so those are the 3 dimensions we have for pressure, but we need to be exhaustive. So we need to look at all our variables and see all the dimensions that we are working with. So the next one is, what is that? Density, right? So density, then we have kilograms per meters cubed. And this is, we can do this faster, this is mass over length to the third, right? Those are the dimensions around density. Next one, and know that it doesn't really matter whether I'm using SI units or not for the sake, if I'm using this method here, right? Because if this were grams or micrograms or any sort of mass unit over any sort of length, it could be miles, it could be kilometers, it will always be mass over length to the third, right? So that's the idea behind dimensions. Next one, we have velocity. And velocity, we know that's meters per second. So our dimensions here, meters, that's length, right? And then seconds, that will be time. Next, we have viscosity. Next, we have viscosity. So if you guys just remember the table we were just looking at before, viscosity, dynamic viscosity is given in newtons times seconds over meters squared. Newtons, seconds, meters squared. And then we can convert, once again, newtons into kilograms, meters per second squared. And that will be over this guy here, so we can eliminate the seconds and that top mass there. Okay, so this guy ends up being kilograms per seconds per meters per seconds. Okay, so that means that this guy here, viscosity, the dimensions of it are some sort of mass over some sort of length times some sort of time. And then we have, keep it close so that we don't still have them. We have the diameter, right? And we know the diameter is measured in meters. So this one is very easy. And it ends up being just length. And likewise, we also have the L, blue. We also have the length of the pipe, and that's also measured in meters. So that's also length that's there. As you guys do, if you guys end up doing this more often and you get used to this, you'll see that whenever we have a situation in which we have this happening, like both of them are exactly the same and simple like that, one of our pi groups will be D over L or L over D, okay? So if you get more used to this, you could just jump one, finding one of the pi groups, because it's definitely going to be one of these. But let's pretend we never did this before, so we're going to do the whole method from scratch, all right? All right, so how many dimensions we have here? We have mass, time, length, okay? And all of them, mass, time, length, mass, length, length, time, mass, time, length, okay? So the only dimensions we have are mass, time, and length, which makes a total of 3 dimensions in all our variables. So we go back to our Buckingham Pi theorem, and where we had the number of dimensions there, we're going to have 3. So that means 6 minus 3 is 3. That means that we have 3 pi groups. Okay, so conclusion is from the Buckingham Pi theorem, we have 6 independent variables and 3 dimensions. So we'll have 3 pi groups. Okay, so it'll be 3 pi groups that explain this situation. Is it possible to use M for meters and M for mass so that they are? I thought I was doing that, but I'll try to make it more. More visible. So like small m versus big M. They're pretty similar, aren't they? Try to do that. All right, cool. So what do we do next? The next thing we do now is try to find these pi groups, okay? So we're going to combine the 6 independent variables to create these 3 dimensionless numbers, okay? Now we could use the step-by-step method, which is the one I showed you before. But what I'm going to do is I'm going to do Same method the convener taught you guys. So we're going to choose the thing we're interested in. Okay, so we're going to choose the pressure drop because that's what we're interested in, plus 3 independent variables. Why 3? Because of this 3 here. Okay, so if we had 4 dimensions, we would choose 4. If we had 2 dimensions, we would choose 2, and so forth. Okay, so I'm going to choose 4 of these guys, and one of them has to be the pressure drop. So pressure drop is going to be one of them. We're going to end up using all of them, so it doesn't really matter what we choose at this point here. And diameter. Okay, so I've chose 3 of those guys, and I'm going to use the pressure drop. And what we need, why choose delta P? Because delta P is the one we're interested in. Okay, because the whole thing is that we're trying to find out how delta P is varying. That's why I left it in yellow at the top there. So I chose that one to be, so that we're going to have that one for sure. And the first one, first pi group, is if we can find pi group for it, then we can leave it aside and we can swap this for the next things that we left behind. Okay, and the whole idea here is the following. I'm going to do the following. Pressure drop times nothing. Velocity to the A, elevated to the A, density to the B, and the diameter to the C. This has to be equal to my time to the 0, that is no time, right? Because to the 0 is 1. My length to the 0, because to the 0 is 1. And my, what's the last one? Mass to the 0, because 0 is 1. So what I'm doing here is I'm saying that I want the multiplication of these 4 guys to be dimensionless. Okay, that's what I'm doing at the moment. And then what we do is we solve this and try to see what will be the coefficient. So we're trying to solve for A, B, and C. All right. So what I'm going to do next is I'm going to sub in the dimensions for each of these guys. So if you guys recall, let's see, my pressure drop was mass times squared length. Mass times square length. Then my velocity, if you guys recall, was length over time. That's to the A. My density, that was mass length cubed, and that will be to the B. And that is my diameter, my diameter is just length. And that is to the C. And this has to be equal to my time to the 0, my length to the 0, and my mass to the 0. For these guys to be, to satisfy this equation, what we do is all the coefficients on M have to be equal, right? All the coefficients for L have to be equal, and all the coefficients for time have to be equal. So we can use that to solve this equation here, and I'm going to do that for one at a time. I'm going to start with time because we only have 2 for time there. So what do we have for time? We have coefficients to the -2 here, right? Because we have on the bottom and it's dividing, so it's equivalent of having t to the -2 as a coefficient. Then we have to the -a. Then we don't have anything over here for time. We don't have anything over here for time, and that has to be equal to 0, which is the coefficient for time over here. Okay, so that tells us that a has to be equal to -2, right? A has to be -2 to satisfy that equation. Next one, let's jump into the next one. Next one, let's do mass, because we only have 2 of the mass. Mass. So my mass, I have 1, then I don't have anything on the next one. Then I have B, and then I don't have anything, and it has to be equal to 0. So that means that my B, for this to be satisfied, is B equals to -1. And last is my length, and that's the one that I have the most things here. And my length is -1. Then I have plus A. Then I have -3B plus C has to be 0. Thankfully, I have A, B already, so I can just plug those guys in. So I'm going to have -1, -2, then -3 times -1, that's going to be +3, plus C has to be 0. Right? So that's CP, therefore has to be 0. Right on. Okay, so what does that mean? So how does that translate? So these 3 coefficients, we can now go back. Let's make it red. We can now go back to when we first created them and check out what we're saying. We're saying that pressure drop times velocity to the, what is a, -2, times the density to the -1, times the diameter to the 0, is a dimensionless number, right? Is a dimensionless number. And this is delta P divided by density velocity squared. So this is our first pi group. This is our first non-dimensional number. And we just found one of our non-dimensional numbers. What you can do now, we're going to do it on the first example. We're not going to do the other ones because I don't want to take too much time on this question. We can do now is actually check to see if it checks out. Okay, so let's just see the units now. I'm going to put normal units now just for the sake of it. Okay, we have newtons over meters squared for our pressure. And then on the bottom, we're going to have kilograms per meters cubed. Then we're going to be dividing by meters per seconds, and that's squared. So that's going to square on both sides here. Okay, so check out what happens. We have this guy takes away these guys. And then we can break our newtons back into kilograms times meters per second squared. And we're going to be left with meters over kilograms over here. And then second squared and meters squared over here. So kilograms, kilograms, meters, meters with these 2 meters, second squared with second squared. So indeed, the number we just created is just on that first pi group there. Cool, next pi group. So what I'm going to do next is the following. Remember I chose these 4 here, sorry. Okay, so what I'm going to do now is I'm going to sub in this guy here. So I'm going to take this guy out. I'm going to put one of the things that we haven't worked yet. We have length and we have viscosity. We can choose, it doesn't matter. By the end of it, we're going to have 3 pi groups regardless. Okay, so I'm going to take that guy out. I'm going to have now, I'm going to do viscosity, density, velocity, and the diameter of the pipe viscosity, just like that. Okay, same thing applies. We're going to do exactly the same principle. We're just looking at these variables here. So my velocity times my density to the A times my diameter to the B times my viscosity to the C equals time to the 0, length to the 0, and mass to the 0. Right? So let's sub those guys in again. What was the velocity? Length per time. Density, length, mass per length to the third. Diameter, length. Viscosity, I don't remember viscosity. What was it? Mass over length time. Mass over length times time. And that is A here, this is B here, and this is C here, and they have to be equal to time, length, mass. All right, let's do this one more time. Again, I'm going to follow the same pattern because check out, we only have time here and here, so that's going to be very straightforward to solve. And I only have mass here and here, that's also straightforward to solve. So let's start with time. So time, I have -1 plus 0 plus 0 minus C has to be equal to 0. So therefore, C equals -1. Mass, the big M for a line. Mass right there. No mass on the first one. Then I'm summing up A, no mass on the third one, and I'm summing up C, that's equal to 0. We have C, right? So that means that A equals coefficient for viscosity will be 1. Next one, horrible M. Next one, length. 1 minus there is 3 minus 1, which is 1. Cool. So we have all the coefficients, right? Once again, we jump back here. Let's do in red so we're consistent with what we were doing before. Once again, we jump up here. So we just created our non-dimensional number, and that will be U times density A, oops, not A, what is A? 1, times diameter, 1, times viscosity, -1. So our non-dimensional number is density times velocity times diameter divided by my viscosity. That is our second pi group. Anybody knows what this is? Does it ring a bell? Yeah, right on. Right, and just, if you guys remember, this is the same thing as Reynolds, right? Reynolds is precisely the forces that are trying to push the fluid forward over the forces that are trying to keep it together. So it's density, velocity, diameter over dynamic viscosity. Okay, two down, one to go. Okay, once again, what I'm going to do is, remember, we first had the we had velocity, density, diameter, and pressure. Then we had velocity, density, diameter, and viscosity. And then to finish off, we need velocity, density, diameter, and length. It's the last one we're missing. And with this, we can find our last pi group. Okay, same process. I'll try to speed it up a bit here. This won't work. Check out why this won't work. Okay, the way that I've created the equation, I'm going to have -1 equals to 0. Okay, that's the kind of things that can happen when you do this. What I'm going to do is I'm just going to flip it. Oops. I'm just going to flip it. I'm going to have L in the beginning, like so. It's not a big deal. You can see this is the same thing. So instead of having this fella here, I'll move it over to this side here. And then we're going to have this as A, B, C. Oops, this one doesn't have any coefficient. A, B, C. Okay. So I'm still analyzing the same 4 dimensions. I just changed which ones have coefficient. You'll see how that's going to affect our math now. Once again, time is minus A equals 0. Mass is B equals 0. And length, that will be 1 plus A minus 3B plus C equals 0. Therefore, C equals -1. What does that leave us with? It means that L times velocity to the 0 times density to the 0 times the diameter to the -1 is a non-dimensional number, and this is the length over the diameter. And this is our third pi group. I told you this was coming right from the start. There we have 2 things that are the same dimension. That's going to happen. Okay, so that's our third pi group just there. Okay, now what do we make of this? What sense can we make of this? Well, there's 2 ways to understand this, to relate this back to mathematical ideas. The first one is that a function of pi 2 and pi 3 has to equal 0 because of the fact that they're dimensionless. The other one is that pi 1 has to be a function of pi 2 and pi 3. Okay, and we can use either or. In this case, we're more interested in this one because we're interested on the pressure drop. Okay, so what does this say? Let's rewrite that with the things that we found. The pressure drop, what was our first pi group? I don't remember anymore. Pressure drop over density velocity square. Pressure drop divided by our density velocity squared is a function of density u d over mu and L over d. Okay, in other words, if you want to rewrite this, the pressure drop is a function of Reynolds and the ratio between the length and the diameter. Okay, so instead of doing all, if you want to find the thing for pressure drop, okay, remember all the experiments we were talking about before? What we can do is we can relate the pressure drop with Reynolds, if we want to, for instance. We can relate it to Reynolds and see what is the behavior that it has according to Reynolds with experiments. Or we can, and then obviously this would be a L over D, this would be a different L over D, and so forth. Or we can actually have a different one, which is Reynolds, for instance, plotted against L over D's and see what's the behavior that Reynolds would have for different L over D's for this particular situation. And then we can have a graph or a table that we can read off values for our pressure drop according to this, which is exactly what is done in mechanical fluids a lot of times. Other than that, the other thing to note is that, well, this is a very powerful method because we don't have to use everything anymore. Instead of that, we can only use certain parameters, non-dimensional numbers that can help us out. But one thing that has to be understood by you guys at this point is that know that what we're coming up with is that the pressure drop is a function of Reynolds and the ratio there. It is not, we don't know what that function is, right? Just by doing this non-dimensional analysis, we don't know what that function is. To be able to know whether this guy, let's get rid of these guys for now, to know, to be able to know if this will be like a linear function or perhaps a quadratic function, or if it's going to be something crazy like that, we need to run experiments to find how the behavior goes against the data, okay? So we know it's a function, but we don't know what that function looks like until we do some experiments around it, okay? So that is the Buckingham Pi theorem. I'm going to hit stop and ask you if you guys have questions around it.